Hey there, hello and welcome to the channel Smart Techie. Today we are going to discuss the topic around designing and architecting any application for the hyperscale world. On that note, I am assuming you are already having prior knowledge. Applications lacking a formal architecture are generally title copper, very difficult to change and no clear picture of the target. As a result, it is very difficult to determine the architectural characteristics of the application without fully understanding the inner characteristics of every component and module in the system. These deployment and maintenance queries are never been easy to answer. Does the architecture scale? What are the performance characteristics of the application? How easily does the application respond to the change? What are the deployment characteristics of the application, and how responsive is the architecture is? It really helps define the basic characteristics and behavior of an application. We can say, for example, some architecture patterns naturally lend themselves towards high scalable applications, whereas other architecture patterns naturally lend themselves towards applications that are highly agile. Okay, so it's a kind of trade-off between agility and the scalability. Knowing the fact, the characteristics, strengths, and weaknesses of each architecture pattern is very necessary in order to choose one on the other that meets your specific business need and goals. So, as an architect, it is utmost important to understand internals, pros and cons, validate the benchmarks, and 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 the one has to really, think of how it will really suit to the different architecture patterns, particularly when it comes to choosing a particular, specific architecture pattern or any approach. I'm pretty much sure at the end of the video, you will get more confident on the different most important architecture patterns and their implementations under the hood. Okay, let's take a deep dive into the topic initially by understanding like what exactly the hyperscale is and why this hyperscale really need. So by definition, as its name implies, right, hyperscale is all about achieving massive scale in computing, typically for big data or cloud computing. Hyperscale infrastructure is designed for horizontal scalability and leads to high level of performance, throughput, and redundancy to enable fault tolerance and high availability. So, hyperscale computing often relies on massive scalable server architectures and virtual networking. So now you'll ask like, okay, why we really need this hyperscale? What exactly the use case behind this? Like, we really talking about like the hyperscale. So yeah, definitely. So there are many reasons why an organization might adopt hyperscale computing. So hyperscale may offer the best or only the way to realize a specific business goal, like providing cloud computing services. Generally, though hyperscale solution deliver the most cost-effective approach to addressing a demanding set of requirements. For example, a uh, big data analytics project might be most economically addressed through the scale and computing uh, density, whatever available in our hyperscale, right? So that is one of the way. So keeping the definition on hyperscale in mind, let's dive into the most important and industry-wide adopted architectures and their design patterns to tackle some of the application problems in the hyperscale world. Okay, so before diving more into the topic, I like to introduce myself. So I'm Sudhir, a certified cloud solution architect professional. and then definitely in enthusiastic software engineer as well. So I also run a blogger and an YouTube channel on latest technology. Last 13 years, I have mostly involved in designing, architecting, and of course hands-on developing the software applications in the hyperscale world. Right, so with the applications of which are really facing towards billions and trillions of public user who are using the software in the day-to-day basis. So you can visit my LinkedIn profile, which I have already given this link over here. So in this topic, what are the things we are going to and we'll talk about the different architecture patterns in the software hyperscale world, and the key concept behind each of the pattern, and what are the things we need to really consider before adopting a specific pattern in our specific use cases. And okay, let's proceed on that. So on that note, if you talk about what are the different architecture patterns, so in a nutshell, we can say like these are the architecture patterns which are definitely we can think of. In the hyperscale world, the first one we can say like the layered pattern. The second one is event-driven pattern. The third one is microservice pattern. Then microkernel pattern, and the space-based architecture pattern. Right. So these are the five type of architecture patterns. We can talk about, but definitely definitely we are going to mostly touch upon three. I would say three most important architecture patterns which are really, coming on the way in the day-to-day life when we are really starting architecting and designing the any use case or any kind of application. These are the most, the most adopted architecture patterns are event-driven pattern and the microservices architecture pattern. Right. So we'll also talk about like what are the pros and cons. Cons of each of these pattern and how they are really comparable with each other in different different use cases. Before getting into those two architecture patterns, I want to touch upon a little bit the layered architecture pattern. So the layered architecture pattern is the most common architecture pattern. So we can otherwise call as this entire architecture pattern, right? We call it like a three-tier architecture pattern or two-tier architecture pattern, or we can say this is an entire architecture pattern. So this pattern is nothing but consist of multiple layers to develop a whole application, right? So we can say like definitely the concept behind this is like components within this layered architecture pattern are organized into horizontal layers, each layer performing a specific role within the application. So although the layered architecture pattern doesn't specify the number of types of layers that must exist in the pattern, most layer architecture normally, it's combination of presentation layer, business layer, persistence layer, and database layer, right? So in some cases, the business layer and persistence layer are combined into a single business layer, particularly when the persistence logic is embedded within the business layer component itself. So thus the smaller applications may have only three layers, whereas larger and more complex business applications may contain 5 or more layers. Okay, so each layer of the layered architecture pattern has a specific role and responsibility within the application. So, for example, a presentation layer would be responsible for handling all user interfaces and browser communication logic as well. Whereas a business layer would be responsible for executing a specific business, which is really associated with the request itself, right? For example, we can say like the presentation layer doesn't need to know or worry about how to get customer data. It only needs to display that information on the screen in particular format. Similarly, the business layer doesn't need to be concerned about how to how to format customer data or display on the screen, or even where the customer data is coming from. Okay, so it's completely a separation of conscience. Okay? So if you, the key concept is, if you notice here in this diagram, each of the layers in the architecture is marked as being closed, right? So this is very important concept in this layered architecture pattern. A closed layer means that as a request moves from layer to layer, it must go through the layer right below it to get to the next layer below that one. Right? So, for example, you can say like a request originating from the presentation layer must first go through the business layer and then to the persistence layer before finally hitting the database layer. Okay, so why not allow the presentation layer direct access to either the persistence layer or database layer? Of course, there is very valid point. The answer to this question is a key concept, which you can say like layer of isolation. What we already talked about, like uh, the separate of conscience, right? So the normally the layers of isolation concept means that changes made in one layer of the architecture generally uh, generally doesn't impact or affect components in other layers, right? Definitely. So those are the concept behind those thing. But when we are really talking about the how can we really bypass any of the layer in this layer architecture? Definitely. I mean. While close layers, cold layers facilitate layers of isolation and therefore help isolate change within the architecture. There are sometimes when it makes sense for certain layers to be open, right? So that's where we can really skip one of the layer and really reach the request from one layer and jump into a layer other layer by skipping one layer in between. So for example, suppose you want to add a shared service layer to an architecture containing common service components, which is really accessed by components within the business layer. So creating a service layer is usually a good idea in this case, because architecturally it restricts access to the shared services to the business layer itself, right? So without a separate layer, there is nothing architecturally that restricts the presentation layer for accessing all those common services, making it difficult to really govern in the access restriction space. Right. So we can say like If we go through one of the example, like let's say like the new services layer would likely reside below the business layer to indicate that that components in this service layer are not accessible from the presentation layer. However, this presents a problem in the business layer is now required to go through the service layer to get the presentation get into the persistence layer itself, right? Which really makes no sense at all, right? So this is an age-old problem with the layered architecture, and it's solved by creating open layers within the architecture itself, right? So as illustrated here itself, the picture, picturized in the screen. So the service layer in this case is marked as open, meaning requests are allowed to bypass this open layer and go directly to the layer below it. So in the following example, definitely since the service layer is open, the business layer is now allowed to bypass uh, and go directly to the persistence layer, which definitely makes sense here, right? So leveraging the concept of open and closed layer definitely helps to define the relationship between architecture layers and request flows, and definitely provides designers and developers with the necessary information to understand the various layer access restrictions that is, exist within the architecture itself. So failure to document or properly communicate which layer is really which layers in this architecture are really open and closed, and why that is open and why that is closed, that definitely results in a tightly coupled and it's very much difficult to test, maintain, and deploy as well, right? So this is one of the example how the request flows from different layer to other layer, and how it's really, and the response also how it's flows uh, from the other side of the layer to the presentation layer. So yeah, definitely, it's one of the example. So it's very much self descriptive. So if you want to analyze this pattern itself, then how we can analyze this, what are the pros and cons, how it's really fits into the space. Like, so if we talk about like what is the agility of the pattern itself, so we can say like the overall agility is the ability to respond how quickly to a constantly changing environment. We can say like, while change can be isolated through the layers of isolation uh, of the different patterns, right? It is still cumbersome and time consuming to make changes in this architecture pattern because of the monolithic nature, of course, right? So we can say like the overall rating is low. So that means it's not too much agile in the frequent changing environment of the application. So if we talk about the how easy the deployment of this kind of application built on this pattern is definitely how simple it is for the deployment purpose. So deployment definitely depending on how you implement this pattern. So deployment can become an issue, right? Particularly for large and larger application or complex applications. One small change to the component can require a deployment of the whole entire application, right? If it's a very large application, then it's very tedious to do so. So resulting in deployments that need to be planned, scheduled, and executed during off hours,
or on weekends. As such, this pattern doesn't easily lend itself towards a continuous delivery pipeline. So further reducing the overall rating of the deployment. So definitely, so as the nature of the application is monolithic, so it's very tricky thing in the deployment space. And what is the testability in the sense like how easy the application to be tested, which is developed in this pattern, right? Because of the components like belongs to a specific layer in the architecture, other layers can be mock or stop, right? So making this pattern is relatively easy to test. So definitely this is the layered application, so every layer can be tested independently. And a developer can mock a presentation component or a screen to isolate testing within a business component, right? So as well as we can also mock the business layer to test certain screen functionalities, right? So in this case, definitely the testability is good in this case. So what exactly the performance of the application built on this type of architecture pattern is uh, so it's very, I mean, very common, right? While it is true some layer architecture can perform well, the pattern doesn't lend itself to high performance applications due to the insufficiency of uh, having go through multiple layers, right? So one request has to go through multiple layers. I mean, for a very minimal request or something like that, right? So it has to go through, I mean, pass through every layer to deal with I mean, a small request or I mean, any kind of request, I would say. So from performance wise, or definitely it's a low. And what we can say, like the scalability, how frequently we can scale, or how well we can scale this kind of applications. So the scalability, definitely we can say it's a monolithic nature. The scalability is a little bit tricky, definitely, because of the trend towards tightly copper and monolithic implementations of this pattern. So applications built using this architecture pattern are normally difficult to scale, right? So you can scale a layered architecture by splitting the layers into separate physical deployment, or replicating the entire application into multiple nodes, right? However, definitely the granularity is too broad, so which makes the application very expensive to scale, right? So it's definitely low. So on the, I mean, on the note of the development, how easy to develop this kind of application built on this kind of pattern is definitely very very good, right? Because everything in one place, so developer no need to stumble around and look for the code and identify what libraries to use, what not to use. So it's very much easy of development, and gets a uh, relatively high score, mostly because this pattern is so well known, and it's not overly complex to implement. So because most companies develop applications by separating skill sets by layers: presence layer, business layer, and database layer, so on. So this pattern become a natural choice for most business application development. So the connection between a company's communication and organization structure and the way it develops software is outlined in what is called Conway's law. So we can say, like, I mean, so this is why we say, like, so this is so much, I mean, very very, I mean, good on the development side of the house. So we can say this. So yeah, so this was all about like the layered pattern. Like I wanted to just touch upon like how easy, I mean, how really the developers or the architects are, I mean, uh, straight getting into this kind of, I mean, architecture pattern, I mean, without thinking anything. And this is also I mean, go to market architecture pattern, but it's really, again, it depends on what kind of application you are going to build and how you are going to build. But I mean, comparing to this, there are very great architecture patterns in place, so which are giving more more benefits out there in the hyperscale world. So
Okay, so let's jump into the architecture pattern which is mostly used in the hyperscale world, and that is highly scalable, as well as I mean widely adaptable, right? So that architecture pattern is nothing but called as event driven architecture pattern. So this pattern is a popular distributed asynchronous architecture pattern used to produce highly scalable applications. It is also highly adaptable and can be used for small applications as well as large and complex applications. So the event-driven architecture is made up of highly decoupled single-purpose event processing and the components that asynchronously receives and process events. Right? The event-driven architecture pattern consists of two main topologies. You can say the first one is mediator topology and the second one is the broker topology, right? The mediator topology is commonly used when you need to orchestrate, right, multiple steps within an event through a central mediator, right? Whereas the broker topology is used when you want to chain events together without the use of central mediator. Correct. So we'll I mean explain a little bit. I mean in this I mean the picture what we are looking for. So because the architecture characteristics of implementation strategies differ between these two topologies, it's very much important for each and every one to know which is the best suited architecture pattern for their specific use cases, right? So if we I mean talk a little more about the mediator topology. So this is useful for events that have multiple steps and require some level of orchestration to process the event, right? For example, you can say like a single event to place a stock trade might require you to first validate the trade, then check the compliance of that particular stock trade against various compliance rules, and assign the trade to a broker, then calculate the commission, and finally place the trade with that particular broker, right? All these steps would require some level of orchestration to determine the order of the steps and which ones can be done serially and which can be done in parallel, right? So there are four main type of architecture components within this mediator topology. The first one is event queue, the other one is the event mediator, the third one is the event channels, and the fourth one is like event processor, right? So the event flow starts with a client sending an event to an event queue, then which is used to transport the event to the event mediator, right? Then the event mediator itself receives the initial event and orchestrates the event by sending signal asynchronously events to event channels, right, which will be execute each step of the process, right? Event processors which listen on the event channels receive the event from the event mediator and execute specific business logic to process that specific event, right? So if you see in this picture itself, like the general mediator topology of the event driven architecture pattern, you can see like common to have anywhere from a dozen of several hundreds of event queues in a particular event-driven architecture, right? The pattern doesn't specify the implementation of the event queue or event queue component. It can be message queue or a web service endpoint or any combination of either event queue component, that means like the message queue and or web service endpoint itself, right? So there are two types of event within this pattern. We can say like the initial event and other one is the processing event. So the name suggests, like, so it's very clear, like the initial event is the original event received by the mediator itself, whereas the processing events are one that are generated by the mediator and received by the event processing component. Correct. So the event mediator component is responsible for orchestrating the steps contained within the initial event, right? So for each step in the initial event, the event mediator sends out a specific processing event to an event channel, which is then received and processed by the event processor. Correct. It is important to note that the event mediator doesn't actually perform the business logic. So whatever the necessary to process the initial event. In fact, so it knows what are the steps required to process the initial event. Correct. So now event channels are used by the event mediator to asynchronously pass specific processing events which are related to each step in the initial event to the event processor. So the event channels can be either message queues or message topics, and although message topics are most widely used with the mediator topology, so that processing events can be processed by multiple event processors as well. Okay, so the event processor components, right? So each of them really contain the application business logic necessary to process the processing event itself. So event processors are self-contained, independent, highly decoupled architecture components that perform a specific task in the application or any of the system. Correct. So while the granularity of the event processor can vary from fine grain to maybe to the coarse grain, so it is definitely important to keep in mind before designing that in general each event processor component should perform a single business task and not rely on other event processors to complete its specific task. So they are completely independent and isolated. So one will pass to another, then once that particular task will be started, then there is no dependency again. So it will do its own work, whatever the business logic written for that particular, applied for that particular task itself, right? So the event mediator can be implemented in a variety of ways. As an architect, one should really understand each of these implementation options to ensure that the solution you choose for the event mediator matches to that specific needs and requirements, right? So the simplest and most common implementation of the event mediator is through open source integration hubs, such as we can say like Spring integration, Apache Camel, likewise, right? So event flows in these open source integration hubs are typically implemented through Java code or some of kind of DSL system, right? So we call it a domain specific languages, correct? So understanding your need and matching them
to the specific, a specific correct event mediator implementation is definitely critical to the success of any event driven architecture using in that particular topology. All right. So using an open source integration hub to do very complex business process or and management orchestration is a recipe for failure, right? So just as is and implementing a BPM, solution to perform simple routing logic, right? So if we can, just jump into this, picture we can see here, right? So let's suppose, go with an example. Let's suppose you have ordered some item from online shopping site, right? And you decided to change the shipping address to for that specific order to a different address, right? In this case, the initial event might be called something like modify order event, right? Then the step involved in processing a modify order event are contained within the event mediator itself. So for each initial event step, the event mediator creates a processing event. We can call as a change address or recalculate the cost for the shipping to a new address, right? So and sends that processing event to the event channel and event processor. So the event processor, is nothing but the order process, order processor and the adjustment processor, right? So definitely, though before executing this, the previous process has to be completed so that it will be run independently, so there will be no dependency. So this process continues until all of the steps in the initial event have been processed, right? So the initial bar over the recalculation of the shipping cost and update order steps in the event mediator, in that particular event mediator, indicates that these steps can be run at the same time, right? That means in parallel. So in this picture, if you can see, once we are getting an event to start dealing with all these processes, then all these processes are very much independent to each other, and they are definitely immutable. They are really not talking to each other. So they have some source of truth. Data came from somewhere, and they will now act according to their applied business logic, right? So that's the one, how the mediator topology really works. Okay, so yeah. Okay, so now let's explore about the broker topology, the second type of topology. The first one we already talk about, like the moderator topology. So now we are going to a little bit deeper about the broker topology. That is the second type of topology in the event-driven microservice pattern, event-driven architecture pattern, I would say. So the broker topology differs from the mediator topology in that there is no central event mediator as such. Rather, the message flow is distributed across the event processors in a chain-like fashion. Actually, one is connected to each other. So in that case, and it seems like a very lightweight message broker, and you can say, for example, like active MQ or RabbitMQ kind of queue message brokers. So this topology is useful when you have a relatively simple event processing flow, and you don't really want to want to have a central event orchestration. So there are main types of architecture components within the broker topology itself. So we can say the one is the broker component, the other one is the event processor component. So the broker component
can be centralized or federated, and contains all the event channels that are used within the event flow itself, right? So on that note, the event channels contained within the broker component can be either message queue, message topics, or it can be combination of both, right? So in that picture, you can always extract that. So we will talk about a little bit more on that picture itself. So as you can see from the diagram, there is no central event mediator component which is controlling and orchestrating the initial event. Rather, each event procedure component is responsible for processing an event and publishing a new event indicating the action it just performed, right? For example, if you say like an event procedure that balances a portfolio of stocks may receive an initial event called stock split, right? So based on that initial event, the event procedure may do some portfolio rebalancing and then publish a new event to the broker called rebalance portfolio, right? Which would then be picked by a different event procedure itself, right? I mean, definitely there may be times when an event is published by an event procedure, but not pick up by any other event procedure, right? So this is very common when you are evolving an application or providing for future functionality and the application extended application itself. So to explain and understand how the broker topology works, we'll use the same example as in the mediator topology we have explained about. Since there is no central event mediator to receive the initial event in the broker topology, the order process process component receives the event directly, changes the shipping address, and then sends out an event saying the shipping address has been changed, right? Then in this particular example, we can say like there are two event procedures that are interested in the change address event, right? So the order process itself and the adjustment process. So those are the two processors. They are really interested once the event to be received once the shipping address has been changed, right? So they are really depend on those change of the shipping address. Otherwise it cannot calculate the cost, or it cannot adjust the cost for a whole order, right? So the order process component recalculates the new cost base on the updated shipping address and publishes an event to the rest of the system indicating what it did. End of the day, it's recalculated the shipping cost event, right? So the order processing component, on the other hand, receives the same change address event, but in this case, it updates an outstanding shipping cost and publishes an event to the system as an update order event, right? So these new events are then picked by other event procedure components, whatever they are waiting for, and the event chain continues through the system until there is no more events are published for the specific initiating event, right? It's a kind of chain of processes. So one is completed and once that is completed, it will throw to one event to the next next process. The next process will be a kickoff, and then that process has been completed, then other processes will be kick off and complete their work. So till the time the initiation the initiated message itself event itself is not completed, then it will keep keep doing the same thing again and again until the event itself is not completed. So the broker topology is all about, chaining of events to perform a business function. The best way to understand the broker topology is to think about like it's a relay race kind of, right? In a relay race, you can see, runners hold a baton and run for a certain distance, then hand off the baton to the next runner, and so on down the chain, right? Until the last, definitely the last runner crosses the finish line. So in relay race, once a runner hands off a baton, she's done with the race. Okay, so this is also true with the broker topology. Once an event process hands off the event, it is no longer involved in the processing of that specific event itself. In nutshell, those processes already completed their work can be reused in some other process initiated by some other other events, right? So there are some of the considerations of, definitely we have to take a look, like when we are planning to really implement this design pattern into our landscape. So the first and foremost is the event driven architecture pattern is a relatively complex pattern to implement, and primarily due to its asynchronous distribution nature. And when implementing this pattern, you must address various distributed architecture issues, such as remote process availability, lack of responsiveness, and the broker reconnection logic as well, in the event of broker and mediator failures, right? So there should be a failovers scenarios need to be taken care properly to make sure like the events are not lost, or the whole process is resilience enough to deal with the deal in the hyperscale world. So another consideration to we can take a look, like when choosing this architecture pattern is a lack of atomic transactions for a single business process, because event process components are highly decoupled and distributed. So it is very difficult to maintain a transactional unit of work across the event processors, right? So for this reason, when designing your application using this pattern, you must continuously think about which event can and which event cannot run independently, and plan the granularity of your event processor accordingly, right? If you find that you need to split a single unit of work, a single unit of work across the event processors. So that is if you are using separate processors for something that should be an undivided transactions, this is probably not the right pattern for your application. All right. So perhaps one of the most difficult aspect of the event driven architecture pattern is the creation, maintenance, and the governance of the event processor component contracts. So each event usually has a specific contract associated with we can say like the data values and the data format being passed to the event processor. This is one kind of contract, we can say, like associated with the event. So it is vitally important when using this pattern to settle on a standard data format. We can say, example, any kind of data format. We have lots of data formats. Out of that, we can say like XML, JSON, Java, plain Java object, and so on, right? And we have to establish a contract versioning policy as well, to right at the start of the start of the event, so that the whole contract will be flow through the one end to other end without any intervention or every process will really abide with that particular contract. Throughout the chain. So yeah, those are the couple of considerations really. Really one has to think of, like when those are the things dealing with. However, definitely when we're talking about the analysis of pattern, so what exactly how the pattern is beneficial and where it can lag. So we'll talk about a little bit on that. Okay, so now let's analyze the event-driven architecture pattern itself. So if you talk about the overall agility of the pattern, so we would go for, it's just a really very good in the agility. So overall agility is the ability to respond quickly to a constantly changing environment. Since uh, event processor components are single purpose and completely decoupled from other event processor components, so changes are generally isolated to one or a few event processors and can be made quickly without impacting other components, right? So that's why it's it's the agility is so good in this pattern itself. So and if you think about like the how the deployment is easy when the application is developed on the base of this event driven architecture pattern, then this will also go and a very good rating because the overall in this pattern is relatively easy to deploy due to the decoupled nature of the event procedure components, right? So they are very much independent to each other. The broker topology tends to be easier to deploy than the mediator topology, of course, primarily because the event mediator component is somewhat tightly coupled, okay, to the to the event procedure. So, but a change a speed changing in an event processor component might also require a change in the event mediator, so there are really tightly coupled, so which really requires both to be deployed for any given changes. So that's why that's why if you compare between the broker topology and the mediator topology, of course mediator topology is little less effective than the broker one, but in general this deployment of the application built on top of this a particular architecture pattern is very good, right? And if you talk about that testability, the testability is little less and low confident, because while individual unit testing is not overly difficult, it does require some sort of specialized testing client or a testing tool to generate events, right? So testing is also complicated by the asynchronous nature of this pattern. So that's always as long as the whole workflow is synchronous, then definitely one data point is really passed through or pass through another step, and they can really executed easily throughout the process. But when it comes to the asynchronous pattern, then definitely there will they come up with the multi-threading system, multi-processing system, so that really a little difficult to write all the test scenarios and have a regression testing on that. So yeah, so and the performance wise definitely it's a very good because while it is certainly possible to implement an event driven architecture that doesn't perform well due to all the messaging infrastructure involved. In general, the pattern achieves high performance through its asynchronous capability. That's why the performance is super high.
So in other words, we can say like the ability to perform decouple parallel asynchronous operations outweighs the cost of queuing and the dequeuing messages, right? And when we jump into the scalability part, so scalability is definitely high as well. These kind of patterns are mainly mainly so adapted because of their scalability. So definitely the rating is definitely high. So scalability is naturally achieved in this pattern through highly independent and decoupled event processors, right? Each event processor can be scaled separately, allowing for fine-grained scalability. Okay, and again, so when I saw like the easy of the, how easy the deployment is, the and let's talk about like how easy the development as well. So definitely developing this asynchronous process, asynchronous whole architecture is little bit difficult and complicated as well. So development can be somewhat complicated due to the asynchronous nature of the pattern, as well as the contracts creating between different event processors, right? So that's where broker failure, the process failure, so that all those things happens. So to deploy those kind of code base, and maintainability is definitely complicated. So it's the rating would go low for the development of this kind of system. So yeah, so we'll see the overall overall comparison, like how it really performs in the hyperscale world comparing to the other one. So let's talk about the next pattern, what we are talking about. Okay, so let's get into and talk talk in depth about the most highly trending, I would say, highly trending architecture pattern in the hyperscale world. So this is nothing but the microservice architecture pattern, right? So this pattern is quickly gain ground in the industry as a viable alternative to monolithic applications and service-oriented architectures. Right? Because this architecture pattern is still evolving, there is a lot of confusion in the industry about what this pattern is all about and how it is implemented. Right? This section of the talk will provide you with the key concepts and fundamental knowledge necessary to understand the benefits and the trade-offs of this important architecture pattern, and whether it is the right pattern for your application or for your use case you are thinking of applying this pattern. So regardless of topology or implementation style you choose, there are several common core concepts that apply to the general architecture pattern. You can say like the first of these concepts is the notion of separately deployed units, right? So it's a separate of concepts, right? As explained in the diagram, each component of the microservice architecture is deployed as a separate unit, allowing for easier deployment through an effective and streamlined delivery pipeline. We can say like the CI/CD process, increase scalability, and a high degree of application and component decoupling within your application. Correct. So perhaps the most important concept to understand with this pattern is the notion of service component, right? Rather than thinking about services within a microservice architecture, it is better to think about service components which can vary in granularity for a single module to a large portion of the application. So service components contain one or more modules, we can say in Java world multiple Java classes that represent either a single purpose function or a independent portion of a large business application. So design the right level of service component granularity is one of the biggest challenges within a microservices architecture. This challenge is, we are going to discuss in more detail in the following service component orchestration section. So in this so another key concept within the microservice architecture pattern is that it is a distributed architecture, meaning that all the components within the architecture are fully decoupled from from each other and access through some sort of remote access protocol. You can say like, okay, it's a JMS or maybe MQ processor and or REST or SOAP or RMI kind of protocols can be used to access between the services. So the distributed nature of this architecture pattern is how it achieves some of its superior scalability and deployment characteristics. Right? So one of the exciting thing about the microservice architecture is that it involves from issues associated with other common architecture patterns rather than being created as a solution waiting for a problem to occur. Right? The microservices architecture style naturally evolved from two main sources, that is monolithic applications developed using the layered architecture pattern and distributed applications developed through the service-oriented architecture pattern. Right. So the evolutionary path from monolithic applications to a microservice architecture style was prompted primarily through the development of continuous delivery. That is nothing but the notion of a continuous deployment pipeline from development to production, which streamlines the deployment of the applications. So monolithic applications typically consist of tightly coupled components, so that are part of a single deployable unit, which really makes it super cumbersome and difficult to change, test, and deploy the application. Hence, the rise of the common monthly deployment cycles typically found in most of the large IT shops, right? So these factors commonly lead to brittle applications that break every time something new is deployed. The microservice architecture pattern definitely addresses these issues by separating the application into multiple deployable units. We can say like the service components, right, that can be individually deployed, tested, and developed as well. Every different services can be maintained or taken care independently in the hyperscale world. So the other evolutionary we can say like best path that leads to the microservices architecture pattern. So when coming to the topologies in this pattern, so while there are literally dozens of ways to implement a microservice architecture pattern, there are three main topologies stand out as the most common and popular. So the first one is API REST-based topology. The second one is application REST-based topology,
and the third one is centralized messaging topology, right? So the first one is the API REST-based topology. So this is useful for websites that expose small self-contained individual services through some sort of APIs, right? So this topology is consists of very fine-grained service components. Hence the name says like microservices, right, that contain one or more modules that perform specific business functions independent from the rest of the services. So in this topology, these fine-grained service components are typically accessed using a REST-based interface implemented through a separately deployed web-based API layer, maybe. Right. So example of this topology includes some of the common single-purpose cloud-based RESTful web services, which can be found by Yahoo, Google, and Amazon kind of organizations. So in other hand, the application REST-based topology differs from the API REST-based approach is that client requests are received through traditional web-based or fat client business application screens rather than through a simple API layer. So the user interface layer of the application is deployed as a separate web application that remotely accesses the separately deployed service components through simple REST-based interfaces. So the service components in the topology differs from those in the API REST-based topology in that these service components tends to be larger, more coarse-grained, and represent a small portion of the overall business application rather than fine-grained single-action services. Correct. So this topology is common for small to medium-sized business applications that have a relatively low degree of complexity. Right. So the third one, the third topology is nothing but called as a centralized messaging topology. So this topology is similar to the previous application REST-based topology, except that instead of using REST for remote access, this topology uses a lightweight centralized message broker. We can say like, for example, ActiveMQ or RabbitMQ. It is vitally important when looking at this topology not to confuse it with the service-oriented architecture pattern, or consider it as a SOA light, right? The lightweight message broker found in this topology doesn't perform any orchestration or any transformation or complex routing. Rather, it is just a lightweight transport to access remote services components, right? So the centralized messaging topology is typically found in larger business applications or applications that requiring more sophisticated control over the transport layer and between the user interface and the service components. So the business the benefits of this topology over the simple REST-based topology that we have already discussed previously are advanced queuing mechanisms, and these are asynchronous messaging, monitoring, error handling, and better overall load balancing and scalability as well. So the single point of failure and architectural bottleneck issues usually associated with a centralized broker that are addressed through broker clustering and broker federation, right? So that you can always achieve by splitting a single broker instance into multiple broker instances to divide the message throughput usually in between the multiple brokers.
so how I mean, when all these things happens, then how we can try to avoid dependencies and the I mean the orchestration anomalies, right? So one of the main challenge of the microservice architecture pattern is determining the correct level of granularity for the service components. So if service components are too coarse grained, you may not realize that the benefits that come with this particular architecture pattern. Those are like deployment, scalability, testability, and loose coupling. However, service components that are too fine grained will lead to service orchestration requirements, which will quickly turn your lean microservice architecture into a heavyweight service oriented architecture again. So which complete it's complete with all the complexity, confusions, expenses, and typically found in those issues in SOA based application, right? So if you find you need to orchestrate your service components from within the user interface or API layer of the application, then chances are that your service components are too fine grained, right? Similarly, if you find you need to perform inter-service communication between service components to the process to process a single request, chances are mostly your service components are either too fine grained or they are not partitioned correctly from the business standpoint. So inter-service communication, when I'm talking about that, that could force undesired couplings between components, and we handle instead through a shared database. Correct. For example, if a service component handling internet orders needs customer information, it can go to the database to retrieve the necessary data, as opposed to invoking functionality within the customer service component, right? So the shared database can handle information needs, but what about shared functionality? If a service component needs functionality contained within another service component or common to all service components, you can sometimes copy the shared functionality across service components, thereby violating the dry principle, don't repeat yourself. Correct. So this is a fairly common practice in most business applications implementing the microservices architecture pattern, trading off the redundancy of repeating small portions of business logic for the sake of keeping service components independent and separating their deployment. Small utility classes might fall into this category of repeated code. Correct. So if you find that regardless of the level of service component granularity, you still cannot avoid service component orchestration, then it's good sign that this might not be the right architecture pattern for your application. Because of the distributed nature of the pattern, it is very difficult to maintain a single transaction unit of work across service components. Correct. So such practice would really require some sort of transaction I would say transaction compensation framework for rolling back transactions, which really adds significant complexity to this relatively simple and elegant architecture pattern. Correct. So when really considering this architecture pattern, so these are the things need to think of. Prior to considering the architecture itself in place. So so when we are talking about some of the considerations, what we really need to take care of, the microservice architecture pattern really solves many of the common issues. Those are found in both monolithic applications as well as service oriented architectures. Since so major application components are split off into smaller separately deployed units, applications built using the microservice architecture pattern are generally more robust, provide a better scalability, and can more easily support continuous integration and delivery purpose as well. So another advantage of this particular microservice architecture pattern is that it provides the capability to do real-time production deployments, thereby significantly reducing the need of the traditional monthly or weekly production deployments, so which really delays the deliverables, correct? So since change is generally isolated to specific service components, only the service components that change need to be deployed, right? So that's very much specific to a specific change to be deployed. So if you only have a single instance of service component, you can always write specialized code in the user interface application to detect an active hot cold deployment or hot deployment and redirect users to an error phase or waiting phase, right? Or obviously we already have some of the more elegant way of deployment process. We can always follow the rolling deployment as well, where there will be no impact to the user, rather it will be automatically deployed in a rolling basis. So alternatively, we can swap multiple instances of a service component in and out during a real-time deployment, so allowing for continuous availability during deployment cycle. So that is nothing but the something that is very difficult to do with the layered architecture pattern, as we always know. So one final consideration would be since the microservice architecture pattern is a distributed architecture, so it sets some of the same complex issue found in the event-driven architecture pattern, which includes contract creation, maintenance, and governance as well. So and also along with that, remote system availability and remote access, authentication, and authorization issues. So that's what the system is like. So when we're going to minimize one of the problem, then there might be very core problems. Staying there in any of the architecture pattern. Okay, now let's analyze some of the attributes in this microservice architecture pattern. So if you talk about how this pattern is how this pattern is good or bad for the overall agility. So definitely this pattern is super agile. So overall agility is the ability to definitely respond quickly to a constantly changing environment due to the notion of separately deployed unit, change in generally isolated to individual service components, which allows for fast and easy deployment. So also applications built using this pattern tends to be very loosely coupled, which also helps facilitate change, right? So if you talk about how easy the deployment is in this particular architecture pattern, so definitely this is also very good in the deployment strategy. So the deployment characteristics of the microservice pattern rate is very high due to the fine-grained and independent nature of the remote services, right? So services are generally deployed as separate unit of the software, resulting in the ability to do hot deployments, right? So any time duration of the day or night or any time without impacting the end user. So if you can talk about like the testability of this particular testability of the application developed on top of this architecture pattern. So this is also, I would say, its testability is very good in this case. Due to the separation and isolation of business functionalities into independent applications, testing can be scoped, allowing for more targeted testing efforts, right? So regression testing for a particular service component is much easier and more feasible than regression testing for an entire monolithic application. That's always we are agree with. So also, since the service components in this pattern are loosely coupled, there is much less of chance from a development perspective, making a change that breaks another part of the application, easing the testing burden of having to test entire application for every small changes. So in case of performance, we can say, like, while you can really create applications implemented from this pattern that perform very well, however this pattern doesn't naturally lend itself to high performance application due to the distributed nature of the microservice architecture pattern. Correct. So and scalability wise, it's amazing, right? That's why it is. So because the application is split into separately deployed units, each service component can be individually scaled, allowing for fine-tuned scaling of the particular application. For example, the admin area of a stock trading application may not need to scale due to the low user volume of that particular functionality, but the trade placement service component may need to scale due to the high throughput needed by most trading applications for their functionalities, right? So that's how how the really it helps in the scalability side of the house. So how easy the development is, like, definitely because of the functionality is isolated into separate and distinct service components, development become more easier due to the smaller and isolated scope. So there is much less chance a developer will make a change in one service component that would affect other service components, thereby reducing the coordination needed among developers or development teams. That really helps in that in the speed of the development itself. So yeah. So on that note, when we already talked about the two of the great architecture patterns for the hyperscale world. So we can definitely compare how really they are benefiting benefiting to the application development, or they're lagging somewhere. So we can see all these things in our next report. And thank you for visiting my channel, and please like and subscribe my channel so that it will give me a boost to get more content on this space, on this hyperscale space. And yeah, have great time. See you in next video. Bye.